Imagine for a moment that you need to install a serious piece of business software.
Okay.
Let's say it's a spreadsheet program you rely on for your entire payroll. But instead of clicking a download link or, even inserting a floppy disk,
Right.
you have to grab a screwdriver, unscrew the actual case of your computer, and physically shove a microchip into the motherboard.
And not only that, but once you manage that incredibly stressful surgery, you open the program and you face an immediate crisis.
A crisis.
A choice. You have to choose between seeing your financial model in a professional, readable format or actually having enough memory left over to input more than a few lines of data.
Welcome to the deep dive, where we take your source material, the documents, the research, the forgotten articles, and we just extract the most important nuggets of knowledge or insight.
And today, we are taking a trip back.
Yeah.
Way back to the early days of personal computing.
We're flipping through the pages of Personal Computer World from January 1985.
We are dissecting a focus article by a guy named Mike Leardat titled, Running a Business on 32K RAM, the BBC Micro Miracle.
And our mission today is to unpack the ambition of Acornsoft, who attempted to turn the beloved BBC a machine known almost exclusively for teaching school children to code into a truly serious business machine.
And they tried to do it using this sophisticated application called ViewSheet.
And crucially, we're going to uncover the surprising and, I have to say, sometimes agonizing trade-offs required.
By everyone. By the developers and the users alike.
To make 1980s business sophistication work on hardware that had an absolute brutal limit of 32 kilobytes of RAM.
It's really the ultimate story of engineering ingenuity born from constraint, The source review highlights this core paradox of the era.
Which is?
You had this increasing sophistication of home computer software, but at the same time, the functional difference between home and business machines was decreasing.
So they were getting closer together.
Exactly. And ViewSheet was supposed to be the proof. It was supposed to prove that the BBC Micro, with its, educational pedigree, could actually stand up in the corporate world.
Acorn was clearly banking on the idea that their home user base, the serious home user as they called them, would sort of graduate into using professional tools.
Bridging that gap.
Exactly, bridging that gap. But as we're about to see, that bridge required some immense technical feats and a pretty hefty financial investment.
It really did.
Okay, let's unpack this journey into 1985 hardware. And let's start with the very first hurdle, just getting the software onto the machine.
Right. So ViewSheet was not a quick project.
Not all.
Acornsoft released this spreadsheet system in October 1984, but the review really stresses it followed 2 years of intensive development.
2 years.
2 years. So this wasn't some hastily ported game. This was a serious commitment to producing an application worthy of any business application.
And what's fascinating to me right away is the collaboration involved. It was published by Acornsoft, but the software wasn't actually written by Acorn itself.
No, it was authored by a third party, another Cambridge company called Protechnic Computers Ltd.
And that name matters, doesn't it?
Oh, it matters a lot. Because Protechnic was also the team responsible for the BBC's highly regarded word processor, View.
So there's a strategy here.
A clear strategic intent. Acornsoft was committed to creating an integrated professional office suite. They wanted View for word processing, ViewSheet for finance, and they later had a database product too.
And using the same developers guarantees compatibility.
Guaranteed compatibility. That's what they were aiming for, this sort of seamless ecosystem.
And to get maximum performance and, I guess, user efficiency, they made a really critical decision about the delivery medium.
Yeah.
This wasn't distributed on a cassette tape,
No.
which was the standard for most home users, right? It involved these load times that could stretch well over 5 minutes.
Accompanied by that high-pitched digital squealing sound that was basically the theme tune of 1980s user frustration.
I remember it well.
Oh, yeah. No, this software was sold as a 16K ROM chip.
A wrong chip.
Read-only memory. It's essentially software that's permanently etched onto silicon. And it was housed in one of the BBC Micro's 5 sideways ROM sockets.
Okay, let's pause on that jargon for a moment, because for a modern listener, sideways ROM sounds like something out of a sci-fi movie.
It does, doesn't it?
What exactly were these sockets and why were they so crucial?
So essentially, the BBC Micro was designed with expandability in mind. But the main brain, the 6502 processor, it could only address a certain amount of memory space directly.
Okay.
The sideways ROM sockets were this brilliant mechanism that allowed the computer to access program memory that lay outside the main 32K memory map.
So it's not memory that has to be loaded from a tape into the machine's main memory.
Exactly.
It's permanently attached and just instantly available.
Precisely. And that is the immense benefit of this approach for that era. The primary advantage, as the review notes, is instantaneous access.
Instant on.
The software is available as soon as the computer is switched on. You flip the power switch, and boom, ViewSheet is ready to go. You bypass the slow storage media entirely.
That's a huge psychological leap forward. And a practical one for productivity. If you're running a small business, you just can't afford to waste 10 minutes every morning waiting for a program to load.
And then there's that second benefit. It's even more critical architecturally, and it really foreshadows the rest of our discussion.
Go on.
Because the program instructions are on that ROM chip, they do not consume any of the internal 2K RAM. All of that precious working memory is, at least in theory, available for data storage.
For the actual numbers and formulas of your spreadsheet model.
Exactly. All of it.
That theoretical advantage is massive.
Yeah.
But before you get to enjoy that instant access and memory conservation, you have to face this really intimidating barrier to entry.
The physical installation process.
This is where the business user had to suddenly become a hardware technician.
Yeah, the product came in a compact box. It had the chip, a pretty substantial manual, a reference card, and a function key template.
And the chip itself was treated with this reverence.
It was protected by an electrostatic-proof sponge mat. Even the packaging was designed to emphasize that this was a serious, sensitive piece of technology.
But the review notes that the whole idea of inserting chips into the guts of your precious computer was, well, it was intimidating for the non-technical user.
Of course it was.
This was the price you paid for instant-on speed. You had to violate your machine.
But the instructions, they tried to be reassuring. They promised it was straightforward.
No soldering required.
Right. Just press the chip in one of the waiting sockets. The whole process, including reading the instructions, supposedly took less than 5 minutes.
I can guarantee you that 5 minutes was probably the most stressful 5 minutes of the entire business day, though.
Oh, absolutely. The friction point here is entirely physical. It requires manual dexterity and a comfort level with electronics that most modern software users would just never tolerate.
And the reviewer described a specific installation headache that just captures the frontier nature of 1985 computing perfectly.
This is my favorite part. The chip must be placed the right way round. There's a notch on the top to show you which way.
Seems simple enough.
But the identifying label on the chip, it often obscured this vital notch.
Wait. So you have this sensitive electronic component, and to make sure you don't fry it, you have to perform this delicate operation of peeling back the manufacturer's own label.
Just to find the physical alignment marker.
That is a truly amazing detail. It's a physical stress test required just to use the software. Because putting a chip in backward could lead to disaster, right?
Oh, you could damage the chip, the computer, or both. It really speaks to the maturity of the market. The software developers had achieved this amazing sophistication, but the hardware packaging and the installation process lagged way behind.
It was a DIY approach to system expansion.
Very much so.
Okay, now let's talk about the downside of the ROM approach, the financial cost. We've established the benefit was speed and memory conservation, but that price tag, it reflected the complexity and efficiency of the medium.
Yeah, ROM chips cost significantly more than cassette tapes or even floppy disks, which pushes up the price of the product.
And the cost was £59.80, including VAT in 1985.
Which is a lot.
To put that into perspective for our listener today, if you adjust for inflation, that is approximately £200 in 2025.
That is a staggering amount for a single application, especially when you compare it to the costs of popular business software on other, more established platforms like Lotus 123 or VisiCalc. It shows Acornsoft was pricing ViewSheet competitively for the professional market.
But creating a serious financial barrier to entry for the casual home user.
The huge barrier.
I have to ask, did the reviewer comment on whether this price point alienated that serious home user, or was the ROM speed and efficiency enough to justify that high investment?
The review implies that the efficiency justified the cost for the target user. It was high, yes, but the result was instant productivity.
So it was an investment.
It was an investment in efficiency, paid for by accepting the physical risk of opening your machine and the high price tag. This wasn't impulse software. It was a tool for someone whose time was valuable enough to warrant the expense.
So you invest the £60, you successfully perform surgery on your computer, you power on, and the spreadsheet loads instantly. Victory.
You'd think so.
But the moment you start to use it, you run directly into the next massive problem, which is the BBC Micro's own crippling memory architecture.
And this is where ViewSheet's engineering genius collides with a fundamental hardware flaw of the BBC Model B.
The 32K bottleneck.
The 32K bottleneck.
Yeah.
And is a fascinating example of how hardware design dictates software utility.
Okay, let's unpack this core limitation thoroughly because it's so important. The BBC Model B has 32 kilobytes of RAM.
Total?
That's it. In a modern computer, the processor memory and the video memory are totally separate. But in the BBC Micro and a lot of 8-bit machines of that era, the memory was shared.
That's right. The spreadsheet data, the numbers, the formulas, the model you're building, it has to share that finite 32K memory pool with the data needed for the computer's visual display.
So it's all one bucket of memory.
All one bucket. We call it bank switching or shared memory. And as I said before, it's a killer for data applications.
Why is it a killer? Give us the why it matters for someone listening today.
Because every single character, every pixel, every aesthetic choice you make on the screen actively reduces the amount of space available for your calculations.
So the better it looks.
The less you can do. The higher the resolution or the more detailed the display, the more memory is reserved for the screen and the less is left for your working model. It forces this direct competition between aesthetics and utility.
So the moment you activate ViewSheet, by typing sheet, if it wasn't the default, you enter the command mode. A simple escape key press toggles you into the spreadsheet display, and now you have to make the most critical decision that will govern the size of your entire spreadsheet.
That decision is the display mode.
The BBC Micro supports 8 of them, numbered 0 to 7. They offer different combinations of resolution, color, character sets.
And ViewSheet was flexible. It could operate in any of them. But the cost of those features was paid in RAM.
Which created the great display trade-off, a choice that dictated the functional capacity of your work. Let's look at the 2 options that matter most to a serious user.
First, there is Mode 3. This is the desirable professional look.
Right. Mode 3 uses a different set of smaller characters, allowing the display to fit 80 characters across the screen.
Which for a business spreadsheet, 80 columns is.
Yeah.
It's essential.
Absolutely. It makes the model look professional, it's clean, and it maximizes the number of columns you can view at once without having to scroll all the time.
But the memory tax for maintaining that 80-column display is prohibitively expensive relative to the 32K total.
How expensive?
The review states that Mode 3 leaves only 9,486 bytes. So roughly 9K available for the spreadsheet data model itself.
9 kilobytes. That is virtually nothing for a complex financial model.
It's tiny.
The benchmark tests in the review, which involved a fairly standard financial projection, showed that in Mode 3, ViewSheet could only accommodate 27 rows of that model before it ran out of memory.
27 rows.
27 rows does not a serious business machine make. It makes it a demonstration model.
Exactly. Now compare that to the alternative, Mode 7.
Mode 7 gives you the capacity, but it takes away the professionalism.
It was the least attractive display mode. It was restricted to only 40 characters per line.
It looked chunky, blocky.
Very reminiscent of the teletext or video text services of the era. Visually, it was just inferior. However, that inferior display was significantly less demanding on the shared RAM. Mode 7 left a massive 24,846 bytes, around 24K for the data.
So we have this really stark contrast. The practical implication is that you, the user, must consciously choose between a professional, readable 80-column display
which gives you only 9K of data capacity.
and a significantly greater spreadsheet capacity in Mode 7, which gives you 24K.
The benchmark tests confirmed it. Mode 7 could handle 72 rows of data. That's nearly 3 times the capacity of Mode 3.
You are literally forced to choose between utility and vanity. If your spreadsheet needed more than 27 rows to operate, you are locked into this aesthetically unappealing, cramped, 40-character display.
That's a huge psychological barrier for a business that's trying to project sophistication.
And crucially, the review points out that this memory difficulty is not a flaw in ViewSheet itself.
No.
It's a flaw in the BBC Micro hardware.
Which suggests that any highly sophisticated application attempting to use 80-column text or graphics on the Model B would face the exact same crippling restriction.
So Protechnik, the developer, was forced to engineer around a systemic hardware flaw.
Exactly. And that leads us to the reviewer's suggested fix, which highlights the true financial commitment required to make the BBC Micro truly professional.
What was the suggested workaround? I'm guessing you had to throw more hardware at the problem.
Of course. The user needed to purchase an external hardware upgrade. something like an Aries RAM board.
What did that do?
This board contained dedicated display memory. By isolating the video memory from the main 32K pool, we call it shadow RAM, the main memory was freed up.
Wait a minute. So Acornsoft is selling a solution that essentially implies buying two expensive pieces of kit,
Mm-hmm.
the 60-pound ViewSheet software plus an external RAM board, just to get the professional 80-column display to work with enough capacity to be useful.
That's the reality.
Was that seen as predatory, or was that just the accepted reality of high-end computing in 1985?
It was just the accepted reality for high-end expansion. The review makes it clear that this Aries board would allow the full 32K of RAM to be available to ViewSheet, even in the desirable Mode 3.
So you could have your cake and eat it too.
You could have a spreadsheet that was large and looked professional. But yes, it dramatically ratcheted up the true cost of sophistication. If you wanted to run a serious business application on a BBC Micro, you were looking at well over £100 in 1985 money,
Or 300 to 400 pounds today.
just for the software and the necessary memory expansion. That's not including the computer itself.
That puts the cost into serious perspective. It makes ViewSheet not just a software purchase, but the entry fee into an entire ecosystem of serious high-end BBC Micro use.
It does.
But once you paid that fee, what did that high-performance, tightly engineered software actually deliver in terms of speed and functionality?
Well, despite the architectural limitations and the memory hurdles, the developers at Protechnic had to ensure ViewSheet delivered powerful functionality.
Yeah.
And, critically, performance that justified the ROM medium in that high price tag.
Let's talk scale first, if only theoretically. The software structure was huge, right?
Yeah, capable of extending to 255 rows and 255 columns. That's over 65,000 cells. But, as the reviewer quickly notes, due to the 8-bit memory constraints we just detailed, it was impossible to use this space fully. The real capacity was determined by whether you were in Mode 3 with 27 rows or Mode 7 with 72 rows.
So the real victory of the ROM approach wasn't scale, it was performance.
It was speed. The software is characterized by its blindingly fast calculation speed.
This is the reward for accepting the physical installation risk.
It is. This ROM code was tight, it was compiled, and it executed directly from the chip without needing to be read into RAM first.
And the review provides specific, measurable data points on that speed, which makes for a great contrast with modern machines.
It does. The recalculation time for that 72-row benchmark model was 10 seconds in the high-capacity Mode 7.
Okay, 10 seconds.
But if you were running the smaller 27-row model in Mode 3, the recalculation time dropped to only 4 seconds.
So what does that work out to?
This equates to a sustained speed of about 7.2 rows processed per second. Now, while that sounds glacial today,
It really does.
it was highly competitive for the time. If you entered a new figure in cell A1, the machine executed the recalculation fast enough that you weren't sitting there tapping your fingers for half a minute waiting for the rest of the spreadsheet to update.
So it felt responsive.
It felt fluid for the size of model the BBC Micro could actually handle.
Beyond the blinding speed, what kind of professional tools did Protechnic manage to squeeze into this incredibly constrained architecture? Let's start with the basics, like formula input.
ViewSheet used standard conventions we still recognize today. For multiplication, for division, and cell references follow the A1 style.
And what's fascinating is the engineering effort they dedicated to minimizing user input. They knew every keystroke counted, especially on keyboards that lacked modern numeric pads or shortcut keys. So ViewSheet employed operator precedences to reduce the need for parentheses.
This is such a subtle but crucial detail for efficiency. If you entered a complex formula like A1, B2, C3, D4, a more basic system might require you to wrap the multiplication terms in parentheses to make sure they execute first.
But ViewSheet was smarter than that.
It was. It recognized that multiplication and division had a higher precedence than addition and subtraction.
So that formula was calculated automatically as A1, B2, C3, D4.
Exactly. This small architectural choice meant fewer errors, less cumbersome formula entry, and faster construction of complex models. It saved keystrokes and mental load.
It really demonstrates that the developers were thinking about the user experience within the limitations of the input mechanism.
Absolutely. The built-in functions were also surprisingly powerful for the time. They covered trigonometry, logic with if-then statements, exponentiation.
But the spreadsheet specials, the functions designed for common tasks, that's where the real brilliance showed.
Yes. The average function, for instance, was described as incredibly versatile.
How so?
It accepted constants, lists, single-cell references, and critically, it accepted rectangular ranges.
The example given by the reviewer is a perfect demonstration of its power and efficiency.
Average, 23, A1 to 1, B to D3.
That single function could calculate the average of 3 totally disparate inputs.
The constant 23, the value of cell A1 minus 1, and the 6 cells in the rectangle defined from B2 all the way to D3.
And that B to D3 notation is the epitome of efficiency born from constraint. Instead of typing B2.D3 or listing every single cell, they use this wonderfully concise shorthand to define a rectangular area.
And similarly, the SUM function was just as neat and concise. The notation A1, A12 would sum the 12 values from A1 down to A12.
This focus on maximizing input effectiveness through compact notation was vital when you're dealing with a slow mechanical keyboard and very limited screen real estate.
And the user interface itself was optimized around this need for quick, efficient input. The screen dedicated the first 4 rows to status information, error messages, or echo text showing what you were typing.
And the rest of the screen real estate was for the spreadsheet itself.
And all of the core editing facilities, row and column insertion, deletion, replication, cell editing, they were all activated by the 10 function keys on the keyboard.
The BBC Micro had those distinctive, often color-coded red function keys, and by combining them with the Control or Shift keys, you could create up to 30 total functions.
And ViewSheet used 23 of those 30 possibilities. It effectively turned the top row of the keyboard into a customized control panel just for the spreadsheet.
The importance of those shortcuts cannot be overstated. You couldn't rely on nested menus or mouse clicks?
Because the BBC Micro wasn't primarily a mouse-driven machine, and traversing deep menus would just slow down productivity.
The function keys made ViewSheet fast to use, not just fast to calculate.
Which, of course, brings us back to the documentation.
Right.
If you have 23 different function combinations, you cannot rely on memory. You needed external physical documentation constantly available.
Which is why that keyboard template supplied with the software was described as invaluable for the expert user. You needed those shortcuts mapped right on the machine at all times.
It was part of the system.
Okay, so we've established that ViewSheet was fast and its notation was efficient. But to truly be worthy of any business application, it needed complex features that belied the machine's 8-bit limits.
And this is where we see the most ingenious structural hacks designed to overcome the physical hardware limitations.
The most impressive of these hacks was the windowing facility.
ViewSheet supported up to 10 windows onto the spreadsheet simultaneously.
10 windows. On a 32K 8-bit machine, that sounds like a joke. How did they even achieve that level of display management, especially when Mode 3 only gives you 80 characters across?
It is a phenomenal feat of coding. The core use was immediate and essential for budgeting or analysis.
Like what?
You could keep crucial data points like the profit line or the running totals visible in one window at the bottom of the screen while you are actively editing the top-level inputs in another window above it.
So no more endless scrolling back and forth.
None.
Walk us through the implementation. How did you, as the user, configure and manage these windows?
Well, only one window has the active cursor for editing at any time. Window 0 is the default. It occupies the entire screen.
Okay.
The user then defines the other windows by setting the top left and bottom right cells. For example, A1 to I19 might be the default. And that definition dictates the size and position of the screen area, not the content.
Meaning you could shrink window 0 down to occupy a small space, say A1 to B5, leaving plenty of room for other windows to be placed beneath it or to the right of it.
Precisely. And the genius didn't stop at positioning. Each of those 10 windows was independently configurable.
In what way?
They could have different column widths, different numeric display formats, different decimal places, and different justifications.
That's a huge feature. You could look at a raw data column in window 1 showing every decimal place.
And simultaneously view the summarized, rounded, currency-formatted result in window 2.
It allowed true customization of the viewing experience for different data sets within the very same model.
And then there was synchronization. This was an advanced utility feature that linked cursor movement across different windows.
Give us a specific example of why a business user would need that synchronization feature.
Okay, imagine you have 2 different budget forecasts running side by side. Maybe 2023 actuals in one window and 2024 projection in another.
Got it.
They're aligned vertically by month. If you move your cursor down to March in the actuals window, synchronization automatically updates the projection window to show March as well.
That's essential for detailed, related data comparison across different sections of a large sheet.
It takes away the cognitive load of manually tracking your position in 2 places at once.
That's a highly polished feature, especially for a machine with such harsh limitations. And they even managed to squeeze in some visualization, correct?
They did. Primitive graphics, they called it. A window option allowed the system to display numbers as asterisks.
So you can make little charts.
By plotting these asterisks horizontally, you could produce simple, immediate horizontal bar graphs right there in the text environment. It was crude, sure, but it showed the desire to introduce data visualization, even when the constraints limited you to pure text output.
Beyond visual display sophistication, ViewSheet allowed for robust customization and security.
Which is absolutely vital for moving from home user to business user.
They allowed selective renaming of rows and columns.
Yes. Initially, it's just numbers and letters,
Yeah.
but you could rename row 10 to sales and columns A to L to represent Jane through DEC.
And the real power was using these custom names and formulas.
Exactly. Instead of typing A29, you could type JEN29. Or for a cell at the intersection of column B and row 10, you could just type E sales.
This dramatically increases the readability of complex corporate models. Looking at a formula that reads Jan sales plus Feb sales is immediately clearer than A10 plus B10.
Much clearer. And they introduced a layer of security through protection. You could protect entire rows or columns against accidental deletion or changes.
Why was this specific protection feature important for the target audience?
This feature was designed for creating what the review calls turnkey applications.
A turnkey application.
It's a standardized template, locked down so that an unskilled user, maybe a clerk entering daily figures, could input data only where necessary. Protection prevented that user from inadvertently deleting the underlying formula or destroying the entire model's structure.
So it transformed the sheet from a flexible tool into a dependable, standardized application.
Exactly.
This all sounds great, but we keep running into the same wall. 32K of RAM. If I need a model with 500 rows, how do any of these features help me?
They don't help the internal RAM capacity directly, no, but this is where the ultimate architectural hack comes in.
Okay.
Disk-based consolidation. Since the BBC's internal working RAM was so incredibly limited, ViewSheet offered auxiliary data storage on disk drives.
This is truly mind-bending engineering for 1985. They essentially created virtual memory or disk-based buffering for the data model.
Yes, and it was structured. It supported up to 5 separate auxiliary arrays of numbers stored on disk.
And these arrays could be large.
Each one could be up to 255 rows and 255 columns. The maximum size per array was 10,710 elements.
So if you utilize all 5 auxiliary arrays plus the active working sheet, what are we talking about in total?
The spreadsheet models could conceptually contain and access over 50,000 numbers in total.
That is the magic number. You are working with a machine constrained to 32K of RAM, but you now have the ability to manage 50,000 discrete pieces of numerical data.
By forcing the vast majority of it out onto the disk drive.
So the active worksheet became the brain performing the calculations.
But the disks served as this massive external memory archive it could constantly query.
And the practical application of this feature, the consolidation operations, is what moved it into true corporate territory.
Absolutely. This allowed a business to read data from different departmental arrays, say one for sales, one for inventory, one for overhead, and then use simple formulas to sum and consolidate all that data into this central active spreadsheet model.
And this capability was new.
The review described it as enabling tasks not normally feasible on an 8-bit micro.
But if the bulk of the data is sitting on a floppy disk, there must have been a severe performance penalty every time you asked the system to read or write data from those auxiliary arrays, right?
There was. And the review acknowledges this openly. Disk access inherently slows down calculations.
So that blindingly fast calculation speed goes out the window.
It can. If your central model needed to pull in data from 4 different auxiliary arrays for a recalculation, the machine would have to pause and spin the disk multiple times. It would totally negate the benefit of the ROM code.
So how did the developers address that inevitable slowdown?
The manual contained optimization hints. Now, the review doesn't detail them explicitly, but those hints likely advise users to structure their model so that disk array access happened as infrequently as possible.
So you'd run a big consolidation routine only once per day, maybe?
Exactly, rather than after every single data entry. It's a classic 8-bit trade-off. Capacity costs you speed, and the manual was required to teach you, the user, how to manage that compromise effectively.
That's a perfect encapsulation of computing in the mid-'80s.
Mm.
The machine gives you the power, but only if you manage its internal limitations with extreme care.
And that leads right into the documentation itself.
Right. Given the incredible complexity we've discussed, the 23 function key combinations, the 10 window configurations, the Mode 3 versus Mode 7 trade-off, and the disk array management, the documentation wasn't just important.
It was the essential bridge between the programmer's genius and the user's practical needs.
And by all accounts, Acornsoft and Protechnik took documentation very seriously.
ViewSheet was supplied with a hefty 140-page, paperback-sized manual, and crucially, it was spiral-bound.
That spiral binding is a small but critical detail.
It is. It means the manual lies flat on the desk while you're typing. In a world without dual monitors or easy digital reference, that physical convenience was a necessity for productivity.
And the manual was intelligently structured, too.
It was divided into two parts, a detailed tutorial and a comprehensive reference section, and they were both well cross-referenced.
The tutorial section was praised for being exceptionally clear.
Yeah, it assumed no prior knowledge of the BBC Micro itself, only that the hardware was set up, and it included screen illustrations to guide the user step by step.
That's a huge point about accessibility and targeting the non-technical professional.
Right.
You didn't need to be a BBC expert or refer to external programming manuals just to run the spreadsheet software. It was designed to be a completely self-contained professional learning experience.
And conversely, the reference section was the deep dive for the expert.
It provided a detailed rundown of every command mode function, every mathematical formula.
Every combination of the 23 function keystrokes. You needed that level of detail to manage the complexity of, say, defining the parameters for 10 printer windows or 5 auxiliary disk arrays.
And alongside the manual, we circle back to those essential reference tools, the reference card and the physical keyboard template.
And we established the template was invaluable for summarizing the function key shortcuts.
But this template, while necessary, introduced a small bit of physical friction into the overall user workflow.
Right. Imagine you're constantly switching between ViewSheet for your calculations and the View word processor for writing your report.
Each application had its own set of 23 shortcuts mapped onto those function keys.
So you had to switch templates constantly.
The reviewer describes this process as a little inconvenient.
Which I think is a very polite British understatement. The template fits under a transparent plastic strip above the function keys. To switch it, you had to physically spring that strip open, remove the old template, and carefully align the new one.
That detail really underscores how tactile and at times frustratingly physical the computing experience was in 1985.
The software was state-of-the-art, but the interface management was still a physical chore. It's a testament to the fact that the platform itself was rapidly evolving beyond its original design intent.
Okay, finally, let's address output flexibility. A business spreadsheet is only as good as the reports it generates.
And ViewSheet mirrored its display power by offering 10 separate printer windows.
So just like the display windows.
Exactly. They were defined by the user with specific cell ranges and formatting parameters. When you issued the print command, all active printer windows were outputted sequentially with their defined formats.
This flexibility was absolutely crucial because of that 80-column display limitation.
Right. You could configure the printout to perfectly mirror the screen display, but more importantly, you could define a printer window that took advantage of larger stationery to print the full width and length of a model.
Something often impossible to view entirely on the 40 or 80-column screen.
And you could get different printout styles, summary, detailed, raw data, charts, just by switching different printer windows on and off. It was like a macro-level printing management system.
And this leads us to the final necessary piece of integration, confirming Acornsoft's strategic goal of an integrated office suite.
Which was that ViewSheet allowed printing to disk or cassette.
Why?
So that the spreadsheet data could be subsequently read as a text file into Acornsoft's word processor, View.
Ah, so it all comes together.
You calculate the numbers in ViewSheet, you print the output to a text file on disk, and then you load that file into View to write your annual report around the embedded figures.
That intercommunication confirmed their success. ViewSheet, View, and the database product Acornsoft was attempting to build a truly seamless, albeit ROM-based, office suite for the BBC Micro.
Ensuring data could flow between professional applications. It closed the loop. It showed they had thought beyond just the spreadsheet itself.
It was a massive effort to push a small machine far, far beyond its weight class.
It really was.
So what does this all mean for us today? Let's try and wrap this up.
Well, ViewSheet ultimately accomplished its goal. It was simple to use, Yet it was fast and powerful enough to be taken seriously as a business application. It nicely complemented the BBC Micro.
Our deep dive into this 1985 review yields, I think, 4 key takeaways about the reality of sophisticated computing in that era, an era defined by constraint and ingenuity.
And the first one is that the trade-off of the ROM revolution was palpable.
How so?
The software was instantly accessible and blindingly fast. It successfully circumvented the excruciating problem of slow tape loading.
But that speed came at a cost. It required you, the user, to physically install a chip with a screwdriver, risking your precious computer, and paying a premium price that translates to £200 today.
Second, RAM scarcity dictated absolutely everything.
Everything. The BBC Micro's shared memory architecture created an impossible choice for the user.
A choice between professional aesthetics,
Yeah.
the 80-column Mode 3, which left a useless 9K for data and functional capacity, the 40-column Mode 7, which provided 24K.
And if you wanted both professionalism and utility, you had to buy a separate, expensive piece of hardware, the Aries RAM board.
Third, we saw these incredible, innovative solutions born directly from those constraints.
Acornsoft and Protechnic successfully overcame the 32K barrier with highly efficient code and advanced structural hacks.
Like the 10-window display, custom naming conventions, and most importantly, the disk-based auxiliary arrays.
That allowed the system to conceptually manage over 50,000 numbers for consolidation operations, a task deemed not normally feasible for an 8-bit micro.
And finally, the true cost of sophisticated computing was so much higher than the sticker price. The purchase price of ViewSheet, £59.80 in 1985, was substantial.
But for any serious business use, the limited internal memory meant that external hardware upgrades like the Aries RAM board were a near mandatory investment. It shows that high-end productivity always came with a hefty tax in the mid-'80s.
This entire story of ViewSheet is just a beautiful example of engineering ingenuity born directly from limitation.
It really is.
The constraints of 32K RAM, and specifically the shared memory architecture, forced developers to prioritize extremely efficient, tight code. They couldn't rely on abstraction or memory hogs. They had to implement extreme structural hacks, like forcing data off into those external disk arrays and making every single calculation count.
It raises an important question that persists even today. We never see that kind of extreme, painful resource management in modern software, where RAM and processing power are practically infinite.
No, developers often just ask the user to buy a better machine.
But when resources are infinite, do we lose the ingenuity and the necessity for the hyper-efficiency that was born from constraint?
I think we lose something profound. In 1985, the limitation wasn't an excuse. It was a design challenge that fostered revolutionary efficiency. Today, resources are often squandered because they're perceived as limitless. The BBC Micro Challenge was to make a small machine feel big, forcing creative solutions that maximized every single byte.
So what did we learn from the BBC Micro's attempt to wear a business suit?
I think we learned that in 1985, software wasn't just code. It was a physical component you had to snap into the motherboard, risking the health of your computer.
We learned that high-resolution text came with a heavy tax, costing you nearly 70% of your available memory.
But mostly, we learned that the drive to organize our lives in rows and columns is timeless, even if you only have 9 kilobytes of working space to do it in.
If you enjoyed this trip through the surprisingly complex pages of computing history, follow or subscribe so you don't miss our next deep dive into another classic issue. Until next time, keep your curiosity sharp and may your pixels stay perfectly aligned.